Okay, this is the video lesson for topic 3.2 on covalent compounds and polyatomic ions. And before we dive into the specifics of covalent compounds, well, really molecular compounds, we want to compare ionic, molecular, and metallic substances. Now, one thing that you probably remember from middle school is the word covalent. That specifically describes the type of bonding. A substance that has covalent bonding, we call it molecular because they exist as individual molecules. So, when we think about the types of elements involved in each of these, ionic compounds have a metal and a nonmetal, and you learned about that in 3.1. Molecular compounds have two or more nonmetals, and metallic substances are made of metals. So I think it's helpful when you're thinking about these properties to have some specific examples in mind that you can refer back to. So for ionic compounds, we could talk about table salt, sodium chloride. Molecular compounds have a lot more variation. So you might think of carbon dioxide, water, sugar, or oil, all of which are molecular compounds. And for metallic substances, you could think about copper wire as an example. Now, once you have these specific examples in mind, it's much easier to come up with their properties. For example, if I asked you the state of matter of an ionic substance, you might not know, but if I asked you the state of matter of salt, you'd probably know that it's a solid at room temperature. So ionic compounds are solids at room temperature. Molecular compounds can be solids, liquids, or gases, as you see from the examples. Metallic substances are typically solid. There's a few exceptions like mercury, but generally solid. Now, only metallic substances are conductors when they're solids, which is why we use metals to make wires and things. So in their solid state, neither ionic nor molecular substances are conductors. Now, when we think about their reaction with water, well, it's not really a reaction, their physical properties with water, ionic compounds generally dissolve in water. Metallic substances generally do not, and molecular substances sometimes dissolve in water. If you think back to previously, CO2, water, sugar, and oil, sugar, for example, we know dissolves in water, and oil we know does not. When they're dissolved in water, ionic compounds conduct electricity, and molecular compounds typically do not. I said not applicable for metallic substances because they don't dissolve in the first place. Now, when we think about their melting points, ionic compounds have very high melting points. So if you think about melting salt, that's something that you haven't done before. Sometimes people think, oh yes, I totally have, but they're really thinking of dissolving it in water. Melting salt would be if you took solid salt and heated it until it was a liquid. And that happens at an extremely high temperature. Molecular substances are relatively easy to melt or boil, so they have relatively low melting and boiling points. And metallic substances generally have high melting and boiling points, although not as high as ionic. Now, when we think about their electron behavior, we know that ionic substances, electrons are transferred. In molecular substances, they're shared, and in metallic substances, we have what's called a sea of electrons. So what this means is that we have these positive metal nuclei, and we have delocalized electrons that have some ability to move around between the nuclei. So when we think about what holds these things together, ionic substances are held together by opposite charges. Molecular substances are held together by shared electrons and bonds, and metallic substances are held together by this attraction between the positive metal nuclei and the delocalized electrons. And I know that those are sort of some new ideas of delocalized electrons, but this is really important as it's what allows metals to be conductive. When we talk about their structure, ionic substances exist in a crystal lattice. Molecular substances exist as individual distinct molecules. And if we were to describe the structure of a metallic substance, we could again use that sea of electrons analogy. Now, when we name molecular compounds, we have to name them differently than ionic compounds. And a good example is thinking about carbon and oxygen. So if I asked you to name a compound of carbon and oxygen, you might have a few ideas. You might think about carbon dioxide, and you might think about carbon monoxide. But just knowing that it's made of carbon and oxygen, you can't figure out the formula because it doesn't rely on charges. So we name molecular compounds differently because they have so many possible combinations that they can have. So when we name them, we use prefixes And those prefixes tell us how many of each atom we have. And I'll go over what they are in a moment. So the general formula for naming, we would use a prefix and then the name of the first nonmetal. Then we'd use another prefix and we'd include the name of the second nonmetal plus the suffix "ide." So for example, dinitrogen pentachloride. Dinitrogen means there are 2 nitrogens. Pentachloride means there are 5 chlorine atoms. So these are the prefixes you should know. 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, like the pentagon, 6 is hexa, like a hexagon, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca, like a decade. So these should be familiar prefixes from like geometry and understanding shapes. Sometimes people do get a little mixed up with tri and tetra, and then with penta and hepta. I assume it's because they both have P's, but just sort of have that on your radar that you should be familiar with these prefixes. All right, so let's look at a little bit of practice. I'll do one example each and then have you pause and try the rest. So dinitrogen trioxide. Well, looking back, we know di means 2 and tri means 3. So dinitrogen trioxide is N2O3. Si2Cl6 would be disilicon hexachloride. So pause for a moment and see if you can try the remaining 4, and then we'll go over them. All right, so there are the answers. Now, one thing you might have noticed is that we don't use the prefix mono on the first nonmetal. So for example, we don't call it monophosphorus pentafluoride, we just call it phosphorus pentafluoride. We only use mono as a prefix on the second nonmetal. So nitrogen dioxide, NO2, it's not mononitrogen dioxide, it's just nitrogen dioxide. All right, so on your guided notes, there's a naming challenge that has mixed up ionic and molecular compounds, and you can try that and then check your answers on the filled in guided notes on Schoology. Now, once they're all mixed together, it's really important to start by asking yourself if the compound is ionic or covalent. Because if you don't do that, you'll be tempted to use the prefixes for ionic compounds. So now that you know these prefixes, you have to be very careful that you only use them on covalent compounds, and that ionic compounds, we're still going to continue to follow the same rules that we used in 3.1. So remember, when we name them, we write the name of the metal and then the nonmetal plus the suffix "ide. And if we have a transition metal, we have to figure out the charge of that transition metal, and we use a Roman numeral to represent that. So whenever you're ready to resume, just press play and we'll talk about the last topic here. So the last topic is polyatomic ions. So polyatomic ions are multiple atoms covalently bonded together that have an overall charge. So there are 6 that you need to know. There are many more that exist in the world, but only 6 that we require you to memorize. So hydroxide consists of an oxygen and hydrogen bonded together with an overall charge of -1. Nitrate is NO3 with a -1 charge. Carbonate is CO3 with a -2 charge. Sulfate, SO4 with a -2 charge. Phosphate is PO4 with a -3 charge. And ammonium is a cation, NH4+. So you can make flashcards. I'll teach you some little tools in class to help you remember these, but it will really help you to learn these and sort of just have that down. Now, when we write formulas with polyatomic ions, we're going to use ionic naming rules. And we're going to treat the polyatomic ions as one unit. If you need more than one polyatomic ion to balance out the charge of the other ion, you'll put it in parentheses and write the number of ions outside the parentheses. So for example, let's say we wanted to make a compound with calcium and nitrate. Calcium has a +2 charge. Nitrate has a -1 charge. So that means each nitrate ion overall is -1. So I need 2 nitrates to balance out 1 calcium. So when I write the formula, I write CaNO3 2. So I put the 2 outside the parentheses to indicate that I have 2 of those NO3 ions. So here's a few examples. Let's go through them. So when we write the names, again, we're going to follow the same ionic naming rules. We're going to write the name of the cation and then the anion. And if we need a Roman numeral, we'll use it. For the first, we don't need a Roman numeral for this, so we would just write sodium carbonate. Sodium is in group 1, it's always +1, and that's why we don't need a Roman numeral. Now, here with iron and sulfate, we do need a Roman numeral because iron is a transition metal. So I know from this formula that 2 irons are balanced out by 3 sulfates. Sulfate has a charge of -2. So that means that in order to balance out 3 sulfates, each iron has to have a +3 charge. So I'd call this iron 3 sulfate. For barium nitrate, that says calcium, it should say barium. BaNO3 2, barium is +2 and nitrate is -1, and potassium hydroxide is KOH. All right, so I want you to pause and try this practice, and then when you're ready to check your answers, press play. All right, so here are the answers. I will tell you it does take a little practice to get comfortable using these, but like everything in this unit, the more you practice, the easier it's going to become. So feel free to come ask me questions. Make sure you're trying the practices on Schoology and taking advantage of extra practice in class, and just let me know what questions you have.